Right, so in this video, we're going to do section 5.4, comparison tests, more tests on figuring out whether or not a series, an infinite series, converges or diverges. So this first one is called the comparison test, often called the direct comparison test. Let a sub n and b sub n, both the sum of a sub n and the sum of b sub n, be infinite series with positive terms. This will be different when things have negative terms or alternating terms, which we'll do in the next video. If a sub n, so the terms of the series, is smaller than or equal to b sub n, and b sub n converges, then a sub n converges. Let's say that again. If a sub n is less than or equal to b sub n, and the sum of b sub n converges, then the sum of a sub n converges. This is the way of saying if you already know something converges, like maybe it converges to the number 5, let's say, and you have something else that's smaller than it, well, smaller than finite is finite. And then if we flip all of those inequalities and think of it the other way around, if the b sub n is smaller than or equal to a sub n, and b sub n diverges, then the sum of a sub n would diverge. So that's just flipping the idea that then if we already know that b sub n diverges, maybe it shoots off to infinity, and a sub n is bigger than b sub n, well, bigger than infinite is still infinite. So that's the direct comparison test. I think that one's a little bit more logical. The limit comparison test, a little bit harder to think about, but very useful tool. Suppose the sum of a sub n and the sum of b sub n are series, again, with positive terms. And let's think about their growth rates or the limit of their ratio, similarly to the ratio test. The limit as n goes to infinity of a sub n over b sub n equals L, where L is some answer to that limit, and then I have 3 conditions based off of what that answer to that limit will be. If that limit is a non-zero finite number, so somewhere between 0 and infinity, but non-zero, so that's strictly not equal to 0, then a sub n and b sub n have the same property. They either both converge or they both diverge. If the limit is equal to 0, and we know that the sum of b sub n converges, where it's important to know b was on the bottom of that fraction, then we know the sum of a sub n also converges. If the limit is equal to infinity, and we know that the sum of b sub n diverges, which it's important to note that b sub n is on the bottom, so the thing that we know should be on the bottom of the fraction. That's going to be useful later on. Then the sum of a sub n would also diverge. Where this would be inconclusive, which would happen once in a while, is if your limit was equal to 0 and the thing on bottom diverged. Then there's no bullet point that talks about that. Really, this test would be inconclusive if that were the case. Okay, let's do an example. So use either the direct comparison or the limit comparison test, and maybe we can write that down. This regular comparison test is often called a direct comparison test to determine whether or not the following series converge. We'll start off with the sum from n equals 4 to infinity of 1 over n minus 4. I'm going to start off by choosing what I am going to compare this infinite series to. So there's lots of different options, and sometimes the first time you try doesn't work and you might have to try again. I recommend comparing to something that looks similar to it. So I'm going to compare it to 1 over n because it looks very similar. But then not only do I know what I'm going to compare it to, I need to know if the thing I'm comparing it to converges or diverges. And so in this case, this one is a harmonic series, which definitely diverges. Okay, so we're going to look at this in direct comparison, and I'm going to do a quick algebra first. We'll come back to that fraction. I know that n minus 3, just the denominators for a second, is smaller than n. I know that algebraically, and then if I were to flip that fraction, I just have to make sure I also flip the inequality, and I can flip all of those fractions. And so now I know that 1 over n minus 3 is bigger than 1 over n. And the sum of 1 over n diverged, so bigger than divergent, that's the direct comparison tells me is also divergent. So therefore, the sum from n equals 4 to infinity of 1 over n minus 3 diverges by the direct comparison test. Ta-da! Let's do another. Let's do another. Same idea. You have to first decide what you're going to compare it to. And I always recommend that you start off with something that looks similar to the series itself. That will make your comparison a little bit easier. So in this case, I'm going to choose to compare this to the infinite series of 1 over k squared because it looks kind of similar to what I've got here. And then I have to just figure out whether or not the thing I'm comparing it to converges or diverges. So I'll do that. This one is a p series. So I know that this one converges because it's a p series with p equals to 2. And remember, for our p series, when p was bigger than 1, it converged. So I know what I'm comparing it to. And I know that I'm choosing to compare it to 1 over k squared, which converges by the p-series test. Now I do the comparison. First, choose what you're comparing it to. Now I do the comparison. So I like to do the algebra first. I think it's easier to start with the algebra. Some people graph them in the graphing calculator or in Desmos. That's another way. I just think the algebra is a little bit easier to convince myself of the comparison. So I'm going to look at those two denominators first. I do know that k squared plus 4 is definitely bigger than k squared. Now, it is bigger than technically or equal to, but that part doesn't really matter. In fact, it actually is strictly bigger than, but either way. Then if I were to flip those fractions, I would get 1 over k squared plus 4 is less than 1 over k squared. Okay, and then what do I know? I did know that the series, the sum of 1 over k squared converges. We already said that from the p-series. So then the 1 over k squared plus 4 is less than convergent, smaller than finite, is still finite. So therefore, the sum from k equals 1 to infinity of 1 over k squared plus 4 also converges by the direct comparison test. I want to point out something. That was the answer to this question. I want to point out something of when the direct comparison test would be inconclusive, because that does happen sometimes. So if this inequality, at the end of the day, it's not in this case, but if that inequality were flipped, if I had something that was bigger than converges, then it's inconclusive, because bigger than converges, bigger than finite might be finite, but it might be infinite. So there are cases where the direct comparison test is inconclusive. So it's really, really important that you pay attention to the direction of those inequalities and really think about, is it bigger than finite? That's inconclusive. Smaller than finite is finite. Smaller than infinity, for example. Like if this inequality were flipped over there, smaller than infinity might be infinity, it might be finite, I don't know. So you have to make sure you pay attention to the direction of those inequalities. Okay, so let's do the next one. So for part C here, I'm actually going to practice with the limit comparison test. But whichever comparison test you use, no matter what, you still have to make a choice at the very beginning. What are you going to compare it to? Always start off with that. And like I said before, I want to compare it to something that it looks similar to. Now this one's kind of harder because this looks really good and ugly. Yeah, so I have k squared plus k minus 1 all over k to the 4th plus 4k squared minus 3. That one looks quite tricky. So it's harder to compare. So what I recommend is that you look at just the highest powers and simplify it. So k squared over k to the 4th is 1 over k squared. Like I really am going to look at just those highest powers, and then that obviously simplifies to 1 over k squared. And then now I know what I'm comparing it to. I have to figure out if that converges or diverges. And in this case, that converges one more time by the p series because it was the same as the one we did before. Okay, so now I'm going to do the limit comparison. When you do the limit comparison test, I'm going to scroll up so we can have it in front of us. I'm going to just copy this down and bring it down to that problem. The important part to notice for the limit comparison test is the order that you're going to do that comparison. So let me copy that, bring it down here. Okay, so the order that I do it really, really does matter, meaning the thing on the bottom for that limit should be the thing you already know the answer to. So in this case, that's my 1 over k squared. So I'm going to do the limit, excuse me, as k. In this case, I am using the letter k. Your limit comparison test was using the letter n. We know that doesn't matter. And so I'm going to do the thing on the bottom is the thing I already know the answer to. Excuse me. And then the thing on the top is the k squared plus k minus 1 over k to the fourth plus 4k squared minus 3. And then I'll do the algebra. So now I have the limit as k goes to infinity. To divide fractions, you flip the second one. So I have k squared plus k minus 1, k to the fourth, plus 4k squared minus 3. But now times k squared over 1. I'm going to actually simplify that and by distributing it all the way across. The limit as k goes to infinity of k to the fourth plus k cubed minus k squared all over k to the fourth plus 4k squared minus 3. And then I'm going to take the limit. And in this particular case, you might notice a couple of things. You might notice that you could do L'Hopital's rule because this is definitely in infinity over infinity. And if that's something that you notice, you're welcome to do L'Hopital's rule. You might also notice some things from Calc 1, depending on how much you remember from Calc 1. But those are the same powers, top and bottom. So if I were to do L'Hopital's rule, I would do it 4 times and I would end up with just whatever those coefficients are in front of the highest power. So 1 over 1. If you're willing to trust my L'Hopital's rule, maybe pause the video and practice L'Hopital's rule. You'd only have to do it 4 times, but you would end up with 1. So I got the answer of 1. So 1, then I have to decide which of those 3 bullet points in my limit comparison test that I got. So did I get somewhere between 0 and infinity? I did. And if that's the case, then that means that they both have the same property. So whatever it is, if they both either converge or diverge, whatever it is, they just have the same property. And in this case, I was comparing it to something that converges. So that means, so therefore, I'm going to write this over here. Therefore, my sum of k squared plus k minus 1 over k to the fourth plus 4k squared minus 3 converges by the limit comparison test. Ta-da! Okay, all right, we got it. Let's do another one. Let's do another one. They're not all easy. I know it's a little bit trickier. The next one, part D, same type of question. The sum from k equals 2 to infinity of 1 over k times ln of k squared. This is a classic one right here where I'm telling you both the direct comparison test and the limit comparison test would work just fine. So I'll just practice the direct comparison test. Maybe you want to pause and practice the limit comparison test and see if we get the same answer. Okay, they both would work. So first things first, though, no matter what, you have to decide what you're going to compare it to. So just like I've been saying, you want to try to compare it to something that looks similar to it. So in this case, I've got a k squared and an ln squared. So 1 over k squared is pretty similar. Which also, again, this one happens to be another p-series, which converges because it's a p-series. So you have to justify your reasoning. So say that it converges by the p-series. And then I'll do the direct comparison. So k times ln, so k squared times ln squared is definitely bigger than k squared most of the time. If k is smaller than I think about 2.5 or something like that, that won't be the case. But for most anywhere I pass that, this is definitely true. So k, because ln is a bigger number eventually. It starts off real small, but eventually it gets actually to be a much bigger number. So then this whole thing becomes bigger than just k squared, which means if I were to flip those fractions, and you can graph that on Desmos if you don't believe me, then I would have 1 over k squared ln squared of k is smaller than 1 over k squared, and 1 over k squared was a series that converged, so smaller than convergent is convergent. So therefore, the sum from k equals 2 to infinity of 1 over k squared times ln squared also converges by the direct comparison test. And you could have done the limit comparison test and you would have gotten the exact same spiel. Ta-da. All right, let's do another one. So same thing for this next one, just to get the extra practice here. I'm going to do another limit comparison test here. But maybe it's actually worthwhile to see Yeah, I'm going to do a limit comparison because we just did a regular comparison right before. Let me do one more limit comparison test. So the limit comparison test, you still have to decide what you're going to compare it to first. So like I said, comparing things to sort of those highest powers are going to be helpful. So in this case, that's 1 over n cubed, which converges one more time by a p-series. If that were a p like the cubed root, that would have been p is 1/3, that would have diverged. Something to remember there. But yeah, I'll do a limit comparison test. So the limit comparison test is you first take the limit as n goes to infinity of 1 divided by the other. And remember, the main part of the limit comparison test is going to be make sure the thing you already know the answer to is on bottom. Otherwise, those bullet points aren't going to help you so much. So just make sure that they're on the bottom. So then I have the limit, as n goes to infinity of, now I'm going to divide fractions is the same thing as flipping the second one. And then I can do L'Hopital's rule 3 times if you want, and I got 1. So then therefore I have the same conclusion, which is the sum as 1 over n cubed plus 3n plus 1 also converges. It has the same property when your limit was equal to 1, converges by the limit comparison test. Ta-da! All right, we're on a roll. Let's do another one. Okay, continuing on. So the sum from k equals 1 to infinity of sine of 1 over k over k. So I'm going to do the same thing. I'm going to start off by comparing this to, let's do the 1 over k, which diverges because it's harmonic. So this one diverges. You could just say because it's harmonic. You could also say because of the p-series test. There's multiple reasons why that harmonic series diverges. You could have done the integral test even to show that it diverges. Okay, so I'll compare that to that, and then I end up noticing something that I'm going to do first is the direct comparison test. Sine of 1 over k is definitely smaller than or equal to 1 over k. And there's a reason why that fraction, that inequality is true. And I want to point it out. Sine is always smaller than or equal to 1. Right? It always is. Sine is always smaller than or equal to 1. It always, always, always is. So that means that sine of anything is smaller than 1. So that's how that inequality is true. But here is a classic example of something that failed. So I had diverges over here, right? The harmonic series diverges. And I have something is smaller than divergent. But smaller than diverges is inconclusive. So that means that my direct comparison test is inconclusive. It didn't work. Now you could try the limit comparison test. I'm not going to do that for you right now. You could, and it would give you the same issue. You would also have an inconclusive. So we got a bit of a problem. So I gotta go above and beyond and think of something different to compare it to. So here's what I'm gonna do. I wanna do a quick little graph off here to the side. And I hope we remember the sine graph, just the sine of x. Like this is y equals sine of x graph. We know that. I also know the graph of y equals x. So you can see that sine of x is smaller than x, right? Just by the graph, So I'm going to start off with that part of the comparison. So I know that sine of x is smaller than x. And I said x, but I wrote something different, right? So sine of 1 over k is smaller than 1 over k. And then I'm going to divide both sides of that equal sign by k, because then the left side of that equal sign or that inequality is now my series in question. I'm going to box this off so you can see that part was done because that part was inconclusive. Okay, all right, sorry about that. Okay, so then I'm going to rewrite this. So now I have sine of 1 over k is smaller than 1 over k, which is 1 over k squared. And so this is a better comparison. So now I've decided to compare to the sum of 1 over k squared, and that one converges by the p-series test. Not only does it converge, I've already got my direct comparison here. My series in question is smaller than converges. So that means, so now I have my conclusion that the sum of sine of 1 over k converges by the direct comparison test. We just had to change what I was comparing it to. And sometimes that's another thing that will happen. Maybe your test is inconclusive. Maybe you want to try a different test, or maybe you want to try to compare it to something different than what was not working before. Cool. All right, let's do another one. Let's do another one. All right, the next one. So the sum from k equals 1 to infinity of ln of 1 plus 3 over the square root. This is one we haven't done yet before, so this is a good one. I'm going to compare it to, remember I told you guys it's always easier to compare it to something that looks similar to, and so p series is a very easy one. So I'm going to compare it to 1 over the square root of k, which if you wanted to rewrite that, that would be 1 over k to the 1/2, which diverges by the p-series test. So that one diverges by the p-series. Okay, now with that ln, it does make the direct comparison a little bit harder. Feel free to do the direct comparison, but oftentimes I find that ln makes that a little bit trickier. So I am going to do the limit comparison test here. So I'm going to take the limit as k goes to infinity of my question, the thing that I don't know, divided by the thing I'm comparing it to, the thing that I already knew either converged or diverged. In this case, it diverged. Okay, and then I'm going to do that limit. Now you might notice as k goes to infinity, 1 over a really large number goes to 0. So 3 over a really large number goes to 0. So both of those fractions goes to 0. And on top, that means I'm left over with ln of 1, which is 0. So I ended up with 0 over 0, which is the time that I can use L'Hopital's rule for. So now I'm going to do the limit as k goes to infinity. Do L'Hopital's rule. Let's do the derivative of the top and bottom separately. The derivative of ln is 1 over that argument times the derivative of the inside, which using the chain rule there, so it would be -3/2 k to the -1/2. And then the derivative of the bottom separately there would be, sorry, -1/2. I did do that wrong. That should have been to the power of 3/2. There we go. -3/2, -3/2. There we go. I just thought of 1 over k to the 1/2 as k to the -1/2, brought the power down and subtracted 1 from the power. Okay, some things are going to cancel, which is nice. That means that this becomes, sorry, I'll keep the colors the same. There we go. The limit as k goes to infinity of, looks like the negatives canceled, the k to the -3/2 canceled, the 3 did not, and I ended up with 3 over 1 plus 3 over the square root of k, and we know that 3 over a really large number goes to 0, so I ended up with 3. And then going back to that limit comparison test, if you want to scroll back up in your notes and you'll see that limit comparison test, and then you can see that if I got a finite number, then the two series have the same property, which is either they both converge or they both diverge. And in this case, I was comparing it to something which diverges, which means my series has the same property of also diverging. So the sum from k equals 1 to infinity of ln of 1 plus 3 over the square root of k also diverges by the limit comparison test. Ta-da! All right, let's just do one more. We're already here. We might as well. I'm going to do another one for this one. I'm going to compare to the thing it looks similar to. And in this case, I have the sum of 5 over n cubed minus n squared times sine of n. So it's always a little bit easier if you look at the higher powers. That's a good starting point. We saw earlier that that doesn't always work, but often that's a good starting point. So the sum of 1 over n cubed is what I'm going to compare it to and make sure we find out if it converges or diverges. In this case, that one converges by the p-series test because p was 3, which is bigger than 1. Okay, and then I'll do the limit comparison test one more time. We've got lots of options here, so we might as well practice multiple ones. You could do the direct comparison test if you'd like. The limit as n goes to infinity. Remember, when you're doing the limit comparison test, you need to make sure that you put the thing you already know the answer to on the bottom. And then that turns into the limit as n goes to infinity of 5n cubed over n cubed minus n squared sine of n, and you are welcome to do a L'Hopital's rule there if you'd like. Or you should notice that I could look at the higher powers, and sine of n is always going to be smaller than 1, so that doesn't really make too much of an impact. So I really can look at the highest powers and I ended up with 5 as the answer to that limit, which falls under the first bullet point for the limit comparison test, which means the two of them have the same property. And I was comparing it to something that converges, which means by the limit comparison test, this series also converges. Ta-da! Awesome comparison test. Thanks, everybody.